Okay, so we're going to look at the homework that was due today. Some of you understood it, some of you struggle with it. This is one of the things that we first discussed at the very beginning of the year. And so it says for number 8, modeling with mathematics. You purchase a car from a dealership for $10,000. The trade-in value of the car each year after the purchase is given by the function f of x equals 10,000 minus 250x squared. What type of function can you use to model the data? So this definitely fits the model of quadratic. If you look on page number 4, they describe function families. They just give the parent functions of a constant, a linear, absolute value, and a quadratic. If you look at the quadratic, it has the parent function is f of x equals x squared. But go ahead and understand this, that a quadratic, we say, is of x. Actually, let me do this. F of x is equal to ax squared plus bx plus c, where a not equal to 0. So you look at this is a quadratic function because the highest degree term is degree 2. So good job for those of you that recognize it as a quadratic. Doesn't matter how they order the terms. If they have this would be the constant c here. This guy here would be your ax squared, the negative 250x squared. So typically, this would be written mathematically. We see more of it written in descending power. You'll see it written like this. You say, okay, f of x is equal to negative 250 x squared plus 10,000. So if you just put quadratic, you answered the question. I noticed that some of you put linear, so let's distinguish between linear and quadratic. Linear linear function is going to fit model this. A plus b, where a is not equal to 0. The highest degree is degree 1. When I say degree, I'm talking about when I talk about the degree of the function, I'm talking about the highest degree of any term. So here, this term here is the highest degree. You look at the variable x, it's of the first degree. This guy here is degree 0 because I could write x to 0, which would be a 1. b times 1 is b. We just don't write it like that. So I want you to understand that to see everything. technically, this is the exact same thing as this. Yes.
What was the quadratic function again?
The quadratic function is this one here. Just fits this model, ax squared plus bx plus c. Now, notice that a can't equal 0 because what kind of function would we have if a were 0 for this guy? Yes?
Is the absolute value?
No. Absolute value is always going to have the absolute value bars. They have to. That's the symbol that are used for absolute value. So if a were 0, this would, you would agree, this would read f of x equals bx plus c. And then therefore, what would the degree of it be then? It were just f of x equals bx plus c. Yes. Yep, it would be linear because it would be of degree 1. So if a were 0, this would be linear. This is why they'll specify, that's why it's specified that a cannot be 0. It's perfectly fine if b is 0 and c is 0. So for example, I'll list some examples of quadratics. So some quadratic examples. I think it's good to see a bunch of examples. So quadratic function examples. So example 1, I could say f of x is equal to 1/2 x squared. This is a quadratic. I want to point out to you guys that you don't have to have an x term. You don't have to have a constant term. The only thing that needs to be satisfied is the fact that you have an x squared term. And the coefficient is real, but they're not going to give you any imaginary coefficients. We're not going to worry about that. So that's one example. Another example you can make up. G of x is equal to 3x squared minus 170. Another example. H of x is equal to 4x plus 15 minus 17 halves x squared. I just want to emphasize again that the order of the terms doesn't matter. This is still a quadratic because the highest term is a square term. There's no x cubed, there's no x to the 4th power, x to the 5th power. Those would not be quadratics. So, how much time do we have left? 8:27, great. So let's talk about this notation here, because I have at least one student that looked at this and it felt like there was some clarification was made where I want to make sure you guys are completely understanding of the details here. This does not mean f times x, as we typically, you guys are familiar with parentheses, typically meaning multiplication when you have a value in front of the parentheses. That's not what this means. This just simply means it's saying I am a function f and my input or my independent variable is x. So let's go into some details there, some notation and terminology. So if I say f of x, and I'm just going to write the general form of a quadratic, or a cannot be 0. What's going on here is this f of x, this is the value of the function. You can think of it like that. You can also think of it as the output. And then as far as the x's go, you can think of these as your inputs. And these would be the independent variable. The independent variable is x, and the dependent variable is f of x. And sometimes you'll see in textbooks where they'll say, let y be f of x. So, but it's the y when we let y be a function of x. So you guys may have touched on this briefly in Algebra 1 at some point, discussing f functions, but let's go over it again to think of what a function is. So a function, a lot of times I'll describe it as like an oven, in the sense that an oven, you put things into an oven, and then there are things that come out after you've done something with the oven, which is, bake. So for example, if I let x be an unbaked casserole, f of x would be a baked casserole. But in very simple terms, non-mathematical terminology here. If I input a loaf of bread into the oven, let's say the loaf of bread is my inputs, I let that be x, I'm inputting loaf of bread. The output, or the value of the function, the output, or the dependent variable, would be baked bread. Let's assume for this example that you cannot have more than one output for any given input. So if I input unbaked casserole, my output can only be baked casserole. It cannot be apple pie. Put it very simply. So again, this does not mean f times x. This is saying the function f, and they're just specifying what the independent variable is. So we say it as f of x, is how you hear it. Yeah. So dependent variable versus independent variable. Here's an easy way to always remember what's what. The dependent variable, f of x, and sometimes we'll say y, because a lot of times we'll say let y be a function of x. Let y be f of x. The dependent variable, y, or f of x, depends on what x is, not the other way around. It makes no sense to say it the other way around. And x is the independent variable because it doesn't depend on anything. It just, a very common independent variable you'll see in problems is time. Time is always ticking, and it happens to always tick at a constant rate under normal conditions. Time doesn't care what's going on in this world. Doesn't care at all. So that you can think of that as being it's independent of other variables. Time is a big one. I think in actually one of the problems we dealt with, there was a basketball being thrown, and the independent variable there was time in seconds. So that's a very common one actually when we put that on there. Independent variable x, and I'll put time is a very common independent variable. A very common one for the independent variable. Any questions about terminology So if we go back to our original problem, so there's some examples. Here, let's discuss this. What's going on here? And again, it doesn't matter which way you arrange it. So the car is purchased, and it seems like every year. So each year that goes by, here's the new value of the car. So if I want to know the value of this car after 1 year, what do you think I might do? If the value of the car is dependent on time, in years, yes.
Make X 1 year.
Yeah, let X be 1 year. Yeah. So we input 1 into X, punch it into a calculator, and I believe 10,000 minus 250 would be what, $9,750. So after 1 year, the value of the car is $9,750. I'm not sure how accurate that is, but based on this model, based on this function, that's what they say it would be. So after 2 years, you want to know what the value of the car is. You substitute 2 into X. And you can see that the value of the car is decreasing, I guess you could say, quadratically. It's not linear. It's not a constant rate of change. Okay? Because what does this look like? Anyone have an idea of what this would look like graphically, just the general shape of it? We discussed this, I think, on the first week. I covered quadratics. And we also touched on cubics, but quadratics. Do you guys remember in your notes maybe the shape of a quadratic? It's actually on that page. They discuss the parent function. Parabola. Thank you. It's a parabola. Now, is this a parabola that is concave up or concave down? Concave down. And how do you know that? What about a parabola that's concave up? As I'm going down, if I start here, it's concave up. But that's not the reason why. Yes.
Because it starts off higher. Yeah.
No. The reason is very simple. When your A coefficient is negative, it's concave down. So this guy here tells me that it's concave down. So I know it's this. I know this is what the function f of x would look like. And I'll put it because A was less than 0. Because A is less than 0. Okay? So they told us that the value of the car started at $10,000. So what would the time be? What would X be at the time that you first purchased the car? If X is the number of years that have passed. 0 would be 0. You just purchased it. So if I plug in 0 into X, I should expect an output of $10,000 because that's what I just purchased the car, the value of the car that I just purchased. And if I let X be 0, oh, okay, it does make sense that it's 10,000. It would be 10,000. Okay. What is that? And what is that called when we let X be 0? That point. It's one of the intercepts. Is it the y-intercept or the x-intercept? If I let X be 0. Yes. Good. It'd be the y-intercept. Think about any point on the y-intercept. Any point on the y-intercept is going to have an x-coordinate of 0. If I let y be 0, when I talk about y, I'm letting let f of x be 0, and I solve for x. What does that value represent? And there's two answers to this. There's the purely mathematical answer, and there's the answer that has an application to the problem. So f of x is the value of the car at any point in time. If I let the value of the car be 0, and I solve for x, what does that value for x tell me? X is the number of years that have passed since I purchased the car. So if I let f of x be 0, that's the value of the car, and I solve for x, that should tell me, and I'll end up having two values for x. Only one of them will make sense, because one will be probably positive, one will be negative. That should tell me how many years must pass before that car is considered to have no value. Let me know if that doesn't make sense. Try letting f of x be 0. Okay? Any questions? Next problem we had to do was on page 10, number 51. Number 51 says, you are playing basketball with your friends. The height and feet of the ball above the ground t seconds after a shot is made is modeled by this function. F of t equals negative 16t squared plus 32t plus 5.2. A, without graphing, identify the type of function that models the height of the basketball. So what would this one be? Is it also a quadratic? Yeah. Because again, the highest term here is a squared term. It's actually right at the function. Okay, so to keep your brains exercised here, I'm going to ask you a very logical question here. And I'm going to read what the problem is talking about again. It says, you are playing basketball with your friends. The height and feet of the ball above the ground t seconds after a shot is made is modeled by the function here. About how tall is this friend of yours, this basketball player? Think about it. 6 foot? Why do you say 6 foot? Because he's a basketball player? That'd be a funny answer, but why do you think 6 feet?
It seems like 6 feet better than 3.
Fit how?
I just seen someone like a really
Okay. Yes?
maybe I think because of the round number.
Yeah. This is it here. Okay. So what would t have to be so that f of t ends up being 5.2? What would the input for t have to be so that we have f of t is 5.2? Very good. Okay, so they start the clock when? When do they start the clock? Right as it leaves the fingers, right? Yeah? Yeah, it would be 0. If you let t be 0, that's the time that the ball is just now leaving the hand. And so that's what I'm saying. The player is probably about 5.2. I don't know exactly, where the ball is left. Depending on what kind of shot he had to make, it doesn't specify. But he's about 5.2 feet. Well, yeah. Let's assume it was from like across the court and he did one of these. I don't know what the name is of that, but let's assume it's like this. I don't know. But okay. Now I don't know the actual height, but I do know that the height of the basketball was 5.2 feet when it was released. Because that's what it says.
So it could have been shorter or taller. And just threw it that way.
What was that noise? Could have been shorter or taller, yeah, but around there, because the basketball was released probably somewhere in this area. So A, definitely it's a quadratic. What's that?
Nothing.
Okay. And it says B, what is the value of T when the ball is released from your hand? Explain your reasoning. Well, T would have to be 0. Because that's when they start the clock. They told us that. I'll just put, because no time has passed. Well, the time has just started. And then part C, it says, how many feet above the ground is the ball when it is released from your hand? And that's actually the first thing that I came across naturally that I want to talk about. And 5.2 feet. So you get, because f of 0 is 5.2 feet. They're saying the value of the function when t is 0 is 5.2 feet. Again, it's just a notation thing. It's just specifying that the independent variable is t. F is a function. Sometimes you'll even hear them or even write in the textbook, we'll just write the letter F, which is fine. I can just say the function F. This is a little more specific, gives a little more information because it tells us the independent variable is t. Any questions about the homework? And one last thing, what would the shape of this graph look like on a XY plane? It'd be concave down. Yep. We call this I can write concave down. Again, that's because this guy right here is negative. Yes. I hope so, but you may use the restroom to pass the thing. Here's something I want you guys to understand. This is a very common thing that students want to do, is they think that this is the actual path of the ball in the air. That's not what this is. This is just measuring the height, strictly the vertical height of the ball relative to time. And I can see how this is a very common mistake because it looks like, and this could be the path of a ball if I threw it up in the air and if I could somehow trace that ball. That's not what this is though. This is strictly the vertical height. This is a measuring in one dimension, strictly vertical height. Because the ball could be going off and there might be the dimension of side by side, side to side, front and back, and up and down, but this is strictly up and down. So let me write that. All right, this function only models the vertical height. The vertical height of the ball. This is a nice shape. Relative to time. Does that make sense? I want to make that clear because I would think that if you're learning this for the first time, you're like, it looks like the pathway, but no, this is just strictly vertical height. And it looks like there is what we would call an absolute maximum for this function. So right here at this point, let's do red. This is the maximum, the max height of the ball. So you might ask, well, why does it look like the pathway of the ball? Why is it a parabola? I know why it's a parabola algebraically speaking, but why is it a parabola just a thing naturally? If we're modeling vertical height of the ball relative to time, why is it just not this? Why does it not look like a straight? Why is that? Yes.
Oh, I was gonna say like when you shoot it and it's up like that, and then into the basket and then yeah.
Mm-hmm.
That's why I kind of got that one. Because like the way that it's shaped.
So you thought that too. When you saw this, it looks like it.
Yeah.
Yeah, but that's not what this is. But why is it this shape?
Because when it goes up, it just measures the x-axis time.
Mm-hmm.
So it just like shows height throughout the height.
That's exactly what it does, but try to go in more detail as to why it's this shape. The reason it's this smooth curve and not just a straight linear, straight line and then a straight line is because think about this. You have gravity, which acts as acceleration against the ball. So the ball at first is going to go up very fast, but then it starts to slow down, right? It doesn't go up, the ball doesn't go up like this, right? The ball goes up like this, and then it speeds up. That's why it's this shape. It's because the rate of change of that ball going up and down is not constant. It's not constant because of gravity. Now, if you're out in space, it could very easily be a straight line, and the ball just keeps moving in deep space, and just keep going and keep going and keep going. There's no gravity out in deep space. That could very easily be a linear model, but not here. When we deal with gravity, we're going to always be dealing with these quadratic models, which makes sense. All right.